Dear students, good morning. This is the sixth module of lesson Light, Reflection and Refraction. In this module, we are going to discuss about image formation of convex and concave lenses. At the end of this module, you can able to differentiate convex and concave lenses, define important terms related to convex and concave lens, differentiate the image formed by these two lenses and derive lens formula and magnification. Now let us discuss convex lens. A transparent material bounded by two surfaces of which one or both surfaces are spherical forms a lens. This means that a lens is bound by at least one spherical surface. In such lenses, the other surface would be plane. A lens may have two spherical surfaces bulging outwards. Such a lens is called a double convex lens. It is simply called a convex lens. It is thicker at the middle as compared to the edges. Convex lens converges light rays. Hence, these lenses are called converging lenses. A double concave lens is bounded by two spherical surfaces curved inwards. It is thicker at the edges than at the middle. Such lenses diverge light rays. Such lenses are called diverging lenses. A double concave lens is simply called a concave lens. A lens, either a convex lens or a concave lens, has two spherical surfaces. Each of these surfaces forms a part of a sphere. The centers of these spheres are called centers of curvature of the lens. The center of curvature of a lens is usually represented by the letter C. Since there are two centers of curvature, we may represent them as C1 and C2 as shown in the figure, or we can represent it by 2F1 and 2F2. An imaginary straight line passing through the two centers of curvature of a lens is called its principal axis as shown in the figure. The central point of a lens is its optical center. It is usually represented by the letter O. A ray of light through the optical center of a lens passes without suffering any deviation. The effective diameter of the circular outline of a spherical lens is called its aperture as shown in the figure. Observe this figure carefully. Several rays of light parallel to the principal axis are falling on a convex lens. These rays, after refraction from the lens, are converging to a point on the principal axis. This point on the principal axis is called the principal focus of the lens. Observe this figure. Several rays of light parallel to the principal axis are falling on a concave lens. These rays, after refraction from the lens, are appearing to diverge from a point on the principal axis. This point on the principal axis is called the principal focus of the concave lens. Our next topic is image formation in lenses using ray diagrams. We can represent image formation by lenses using ray diagrams. Ray diagrams will also help us to study the nature, position and relative size of the image formed by lenses. For drawing ray diagrams in lenses alike of spherical mirrors, we consider any two of the following rays. Our first case is as shown in the figure. A ray of light from the object parallel to the principal axis after refraction from a convex lens passes through the principal focus on the other side of the lens. In case of a concave lens, the ray appears to diverge from the principal focus located on the same side of the lens as shown in the second figure. Our second case is a ray of light passing through a principal focus after refraction from a convex lens will emerge parallel to the principal axis as shown in the first figure. A ray of light appearing to meet at the principal focus of a concave lens after refraction will emerge parallel to the principal axis. This is shown in the second figure. Consider our third case. A ray of light passing through the optical center of a lens will emerge without any deviation. This is illustrated in the given figure. Our next topic is image formed by convex lens. The first position of our object is at infinity. In the case of a concave mirror, you can observe that the parallel rays incident on that lens and it converges at a single point after refraction, that is at f2. So we can say that the object is at infinity, the image is formed at f2 or the second focus, and the image is point sized and diminished. Next, the position of object is beyond C1. Here there are two centers of curvature. First one is C1 and C2. So we can say that the object is placed beyond C1. So here you can observe that a parallel ray is after refraction passing through focus, and when a ray is passing through the optical center, it cannot have any deviation. So these two refracted ray meeting between f2 and 2f2 or f2 and C2, you can observe that the size of the image is diminished and the image is real and inverted. The next position of our object is at 2f1 or C1. You can observe that when a parallel ray after refraction passing through the second focus and also when a ray is passing through the optical center cannot have any deviation. These two refracted rays are meeting at C2. So we can say that the image formed at C2 and it is same size as that of object in the case of a concave mirror. Here the image is real and inverted and same size as that of object. Then our next case is the object is between 2f1 and f1 or C1 and f1. Here the same rays, parallel ray passing through f2 and then another ray is passing through optical center cannot have any deviation. These original rays meeting at the other side of this lens and formed an enlarged image, but it is the meeting place of these two original refracted rays. So we can say that it is real and inverted image and also it is enlarged image. Our fifth case is the object is at f1. Here also a parallel ray after refraction passing through the second focus or f2 and a ray is passing through the optical center cannot have any deviation. But you can observe that here the ray is not meeting here, but it should be meet at infinity. So we can say that a real and inverted and also very enlarged image is formed at infinity, and it is the original meeting place of these two refracted rays. So it is real and inverted image. In our last case, the object is placed in between f1 and the optical center of this lens. So here we can choose a parallel ray after refraction passing through the f2 and the same ray, the optical center, that is passing through the optical center cannot have any deviation. But you can observe that this refracted ray cannot meet at infinity. So we can extrapolate this refracted ray at the same side of this object. Here an erect virtual image is formed because the actual ray is not meeting and formed any image. Here the extrapolation of this refracted ray forms an image that is virtual and erect. Students, please observe this table carefully. This table gives nature, position and relative size of the image formed by a convex lens for various positions of the object we already discussed. Now let us discuss the image formed by a concave lens. Here we are studying only two cases because concave lenses are always formed virtual, erect and diminished image in the first side of this lens, that is whereas the object is placed at the same side it forms virtual, erect and diminished images. This table provides the nature, position and relative size of the image formed by a concave lens. Now let us discuss sign conventions for spherical lenses. This sign convention similar to ones used for spherical mirrors. So here instead of pole we are choosing the optical center. Optical center as our origin. So from optical center to left side, the distance from optical center to left side is always considered as negative and optical center to right side is always considered as positive, and the height of the object above principal axis is positive and below principal axis is negative. Now let us derive the lens formula. As we have a formula for spherical mirrors, we also have formula for spherical lenses. This formula gives the relationship between object distance u, image distance v and the focal length f. The lens formula is expressed as 1 by v minus 1 by u equal to 1 by f. Next, the magnification of spherical lenses. The magnification produced by a lens similar to that for spherical mirrors is defined as the ratio of the height of the image and the height of the object. It is represented by the letter m. If h is the height of the object and h dash is the height of the image given by a lens, then the magnification produced by the lens is given by m is equal to height of the image by height of the object, that is equal to h dash by h. And also magnification is produced by a lens is also related to the object distance u and the image distance v. This relationship is given by magnification m is equal to h dash by h, that is equal to v by u. Students, today we discuss about spherical lenses, image formed by spherical lenses, lens formula and magnification. Hope you understood this portion. Read your textbook thoroughly. Thank you.